Welcome back to the deep dive. So you've handed us a stack of research, and it's a literal complex roadmap designed for aspiring cloud architects. Our mission today is, well, to give you the ultimate shortcut.
Exactly. We're going to try and cut through the noise.
We're not just going to list Google Cloud Platform or GCP services.
Yeah.
We're going to synthesize all this material. The goal is to provide the essential knowledge you need to start architecting intelligent solutions.
Right. And it's not just about understanding what the tools are. It's about knowing when and, more importantly, why you should pick one over another.
I'm glad you said that because that's the whole game, isn't it? The why.
It absolutely is. This deep dive is foundational. We're going to organize the truly vast universe of GCP into its core pillars: compute, storage, and databases.
Okay.
And by the time we finish, you should be able to look at an application requirement, something like high availability or massive scale or real-time consistency, and immediately know which 2 or 3 GCP services are even candidates for the job.
So we're building a mental model, a framework for decision-making.
That's the perfect way to put it.
Okay, so let's unpack this with the absolute basics. When people hear Google, they instantly think of their massive end-user products: Search, Gmail, YouTube. How does that reality define the core identity of Google Cloud Platform?
Well, that connection is the core insight. It's not just marketing. GCP is defined by running on the exact same infrastructure that powers those global scale products.
It's the very same, not like a separate wing of the data center.
The very same. We're talking about an infrastructure that handles billions of users, petabytes of data ingested every single hour, and uptime that's measured in years, not days.
Wow.
So when you spin up a service on GCP, you are, in a very real sense, getting access to that proven, hardened, global capability.
That's a massive competitive advantage right out of the gate. You're not buying new, untested infrastructure. You're buying capacity on something that's already been, well, battle-tested at a scale most companies can't even imagine.
Precisely. And the platform's breadth reflects that. I mean, while we're concentrating on the core triad today, compute, storage, and databases, it's really important to remember the platform extends far beyond that.
Right.
You've got networking, huge specialties in big data, some of the best machine learning services on the planet, and IoT. It truly is a comprehensive suite, and it's built for the most demanding workloads because, well, Google's own workloads are the most demanding.
So we understand the pedigree, the massive infrastructure, but, every major cloud provider has a list of benefits. Let's move past the generics and really unpack the core value proposition. What are the key differentiators that make GCP stand out strategically?
Okay, yeah, let's do that. We can highlight 5 foundational advantages, but I think we need to explain how GCP delivers them uniquely rather than just, listing the buzzwords.
Agreed. Let's start with the big one, scalability.
Right. So scalability. While all cloud scale, that's kind of the point of cloud. But GCP is inherently built for hyperscale and elasticity. That comes directly from its experience handling massive, unpredictable traffic spikes on services like YouTube.
You mean like when a viral video drops and usage goes up by 1,000% in an hour?
Exactly that. The architecture is designed to handle that. Resources can be scaled virtually instantaneously, both up and down, which is just as important.
That's the baseline.
Yeah.
Now let's talk money, because cloud costs are often the most complex and frankly the scariest element for any business. How does GCP uniquely approach cost effectiveness?
This is a huge differentiator. GCP's pricing model is, I find, extremely competitive and transparent. But the key features here aren't just, low sticker prices. It's the automatic financial rewards for commitment and consistent usage.
Automatic.
Yes. They pioneered something called sustained use discounts. This means the longer you run a VM in a given month, the cheaper its hourly rate gets automatically. You don't have to sign a contract. You don't have to call anyone. It just happens.
Okay, so it rewards consistency without forcing you into a long-term plan.
Precisely. But if you are ready for a long-term plan, you have committed use discounts. You commit to using a specific level of resources for 1 or 3 years, and you get a significantly larger reduction in cost.
And that's all about predictability for budgeting.
It is. This model provides budget predictability that rivals often require extensive paperwork or, complex reservation processes to achieve. It feels more user-friendly.
That really shifts the conversation from haggling for a discount to just focusing on efficiency. The discount is sort of baked into the model. Okay, moving to the tech side. The third differentiator is innovation.
Absolutely. When you think Google, you think cutting-edge R&D.
Right.
And that investment in innovation is non-starp, especially in the areas where Google's core business leads the world,
Mhm.
machine learning and data analytics. When you see breakthroughs coming out of Google AI research, they are integrated into services like BigQuery and Vertex AI very, very quickly.
So you're not just buying a platform, you're buying into an R&D pipeline.
That's a great way to think about it. You're buying a platform that is consistently incorporating state-of-the-art technology, particularly these AI and ML services that are designed to run at the scale of Google itself.
And since they run services like Gmail and YouTube globally, I have to assume their geographic footprint is enormous. Which brings us to global infrastructure. But again, how is this different from their competitors?
It's defined by their global infrastructure, and this part is critical, their private fiber network.
Oh, okay. Tell me more about that.
So GCP operates an extensive network of data centers, but the data traveling between these regions often uses Google's own private subsea fiber optic cables.
So it's not going over the public internet.
A lot of it isn't, no.
Yeah.
This means the infrastructure connecting your services globally is engineered for incredibly low latency and high security. It allows you to deploy applications closer to your users all around the world with exceptional, predictable, low latency. This is a key selling point for global gaming, for media, for e-commerce.
So it's not just where the data centers are located, but how they are connected that really matters. That's a huge point.
Exactly. And finally, the fifth point is security. Just like the infrastructure, the security posture is inherited from the organization that has to defend against nation-state attacks on services like Gmail every single day.
That's pretty good pedigree.
It is. GCP provides a secure environment by default, backed by robust controls, multiple layers of defense, and a huge number of compliance certifications. You're leveraging that massive internal investment to protect your own assets.
That's a really robust foundation. We have scale, transparent cost-effectiveness, rapid innovation in AI and ML, predictable global reach through that private network, and inherited world-class security. With that understanding of the platform's strategic advantages, let's pivot from the why of GCP to the how of the crucial set of compute tools that run your actual code.
Okay. So when we talk about compute services, we're really talking about execution environments. And the critical architectural decision, the first one you have to make, is where you place yourself on the control versus management spectrum.
Right.
Do you want maximum control, which is infrastructure as a service and thus maximum responsibility? Or do you want the cloud provider to manage everything for you, which is serverless, in exchange for giving up some flexibility?
Okay, so let's start at the ground floor. Where do we begin when an organization needs maximum control over the stack, the IaaS layer?
That would be Compute Engine. This is GCP's IaaS offering for creating and managing virtual machines, or VMs. When you hear Compute Engine, you should think virtual servers.
It's the traditional path, right? For anyone coming from an on-premise data center, this feels familiar.
It's the most familiar path. You're essentially renting a server in Google's data center.
And the defining characteristic here is that full control. What does that specifically entail for the user? I mean, what do I actually get to do?
It means you dictate everything. You choose the specific machine type from memory-optimized machines for large databases to compute-optimized machines for heavy scientific workloads. You choose the operating system, you install the application stack, you set up the security hardening, you manage the patch schedule.
Over control.
For an organization that needs very specific, maybe even legacy software configurations or direct OS access for, say, a monitoring agent, Compute Engine is really non-negotiable.
Okay, let's make this concrete. Give us a scenario where this level of control really justifies the management overhead.
Okay, imagine a financial trading firm. Let's call them Global Trades. They need to run a proprietary, highly optimized quantitative trading engine.
Okay.
This engine requires a specific Linux kernel version, and it relies on low-latency local SSDs attached directly to the VM for fast scratch space. They need maximum isolation and completely predictable performance. Compute Engine is the only option here, because they need that fine-grained control over the underlying hardware resources, the machine family, the OS settings, all the things that higher-level, more managed services abstract away from you.
But, and this is the big but, if they move to Compute Engine, they were accepting the responsibility for everything above the hypervisor.
Everything. OS patching, software installation, security configuration, monitoring. That's a heavy lift.
Right. That's the counterpoint to IS.
It is. If Global Trades wanted a faster time to market and didn't have those really stringent hardware requirements, choosing Compute Engine introduces, frankly, a lot of unnecessary operational complexity. They have to staff and maintain teams dedicated to server management, which is often not their core business value. Their business is trading, not patching servers.
Right, that makes perfect sense. Okay, so moving up the stack from raw VMs, containerization via Kubernetes has, it's completely revolutionized how applications are built and deployed. But managing raw Kubernetes is notoriously difficult. How does GKE simplify this?
Right, so that brings us to Kubernetes Engine, or GKE. It is a managed Kubernetes service. Kubernetes itself is an open source system, actually originally developed by Google, that orchestrates containers. So for GKE, you should think managed containers.
Okay, managed containers.
And a strategic insight here is that GKE's value is not just the orchestration, it's its foundation in open source Kubernetes. That significantly reduces vendor lock-in compared to more proprietary platform as a service offerings.
That's a huge business insight. The open nature of the tool itself provides portability. So, okay, what's the management division of labor here? What does Google do, and what do I do?
It's a great question. Google manages the Kubernetes master components, what's called the control plane. That includes the API server, the scheduler, the etc. data store. Basically, that's the brain of the cluster.
And that's the hardest part to run reliably.
It is the hardest, most failure-prone part of a Kubernetes cluster. You, the user, still manage the worker nodes. Those are the VMs where your containers actually run. But even there, GKE offers features like auto-scaling and auto-repair for the nodes to reduce that management burden.
Okay, so let's go back to global trades. Let's say they decide to decompose their monolithic trading platform into microservices. One for pricing, one for execution, one for logging. GKE seems like the ideal choice for deploying those individual services.
Yes, absolutely. Because GKE handles the complex networking, the service discovery between those microservices, the scaling, the rolling updates for all of those distributed components, if the pricing microservice suddenly sees 10 times the traffic because the market is volatile,
GKE just scales it up.
GKE scales up the required containers instantly without human intervention.
But surely using GKE introduces its own complexity. Kubernetes has a steep learning curve. When is GKE just overkill?
It's definitely overkill if the application is simple or monolithic. Setting up and maintaining a GKE cluster requires significant Kubernetes knowledge. If you only have one single web service that occasionally needs to scale, the operational overhead of managing the node pools, understanding all the YAML manifests, handling the networking within the cluster, it often outweighs the benefits of containerization.
So you need the application complexity to justify the operational complexity of Kubernetes.
That's the rule of thumb, yes.
Okay. So let's look at the true platform as a service, the PCS experience. This is where we surrender a lot of control for speed and simplicity. This is App Engine.
App Engine is the classic GCP PASIS offering. The goal here is the highest level of abstraction. It allows you to build and deploy web applications without any direct server management.
None at all.
None. You upload your Python or your Java or your Node.js code, and App Engine automatically provisions, scales, load balances, and secures it. For App Engine, you should think managed web apps.
That sounds almost restrictive. If I'm coming from a VM, why would I limit myself to App Engine's specific runtimes and its execution environment rather than using GKE, which gives me ultimate flexibility? What is the real trade-off I'm making for that speed?
That is the critical question, and the answer is nuanced. The trade-off is environment flexibility versus zero operational overhead. And App Engine actually has two different environments to manage this trade-off.
Okay.
You have the standard environment. This offers extremely fast scaling. It can scale from 0 to thousands of instances in seconds, but you are limited to specific Google-defined runtimes. It's a very controlled, sandboxed environment. This is truly fire and forget serverless.
And the other one?
The other is the flexible environment.
Yeah.
This runs your code in custom Docker containers, a bit like Cloud Run, which we'll get to. But Google manages the VMs those containers run on. This gives you way more customization. You can use any language, any library, but it slows down the scaling and it can't scale fully down to 0.
Okay, so if a small startup, let's call them Fast Launch, needs to deploy a simple promotional website built in Python, and they need it running in minutes with absolutely no operational headaches, App Engine Standard is perfect.
It's perfect. They accept the runtime limitations in exchange for maximum speed and cost efficiency because it scales to 0 so they don't pay when no one is visiting the site.
Right.
But the counterpoint is crucial. If fast launch requires root access to the underlying OS to install a specific monitoring agent, or they need to run some binary that App Engine doesn't support in its sandbox, then App Engine is immediately unusable.
You can't just SSH in and install something.
You cannot. You pay for the speed and the zero management by adhering to Google's rules.
Got it. Okay, now we get to the current darling of cloud development, serverless. The billing model shifts dramatically here. You only pay when the code actually runs, scaling all the way down to zero cost when it's idle. This has completely changed how developers approach certain tasks.
It really has. And the serverless space in GCP is kind of bifurcated. It's based on the complexity and duration of the task you're trying to run. We start with the simplest form, function as a service, or FACE, and that's cloud functions.
Cloud functions. So these are event-driven code snippets. How should we think about their architectural purpose?
The best way to think about them is event triggers. They are designed to respond to events happening elsewhere in GCP. A file appears in a storage bucket, a message arrives on a queue, or a simple HTTP request comes in.
And they're for small atomic pieces of logic.
Exactly. The classic use case is, say, a media company uploads massive 4K video files to cloud storage. A cloud function instantly triggers, and it automatically creates compressed 1080p and 720p versions of that video for immediate delivery to different devices.
That's workflow automation at its finest. It's glue code.
It is. It's a glue that connects services together. But what's the hard limitation on cloud functions?
I'm guessing time.
They are short-lived. They have strict execution time limits, usually around 9 minutes maximum. If that same media company tried to use a cloud function for a complex multi-hour video rendering job, it would just fail. It would time out.
So they're tailored for immediate response and service chaining, not for long-running computation.
Exactly right.
Okay, that brings us to Cloud Run, which to me feels like the perfect bridge. It seems to combine the financial efficiency of serverless with the portability of containers.
I agree. Cloud Run is, in my view, the strategic masterpiece of the compute portfolio. It runs stateless containers on a fully managed platform. The user just packages their entire application environment inside a container image.
Any container.
Any container. And Google manages everything else, including that crucial auto-scale to zero capability. The way to think about it is container plus serverless.
So our startup, Fast Launch, instead of forcing their application into App Engine's specific Python runtime, they could just containerize it, deploy it on Cloud Run, and get the exact same cost efficiency benefits.
Yes, and that is the critical differentiator from App Engine standard. Cloud Run accepts any containerized application, any language, any operating system dependency, as long as it exposes an HTTP interface. It offers the flexibility of GKE containers without the operational overhead of managing a cluster.
That sounds almost too good to be true. It's ideal for APIs, backend services, web applications.
It is. It scales rapidly and efficiently. But surely, as you said, there's a catch.
There's always a catch.
The primary catch is that, being serverless, it's inherently stateless. This means it's not the best option for applications that require dedicated persistent storage attached directly to the instance, like a physical hard drive.
Right, you can't just write to the local file system and expect that data to be there on the next request.
No, because the next request might be served by a completely different container instance. You have to integrate with external storage and database services. And while the cold start time is minimal, it does exist, which is different from a pre-warmed VM sitting on Compute Engine waiting for traffic.
Wow. The distance between the full control of Compute Engine and the complete abstraction of Cloud Run, just in terms of management overhead, is staggering.
It is.
It's like moving from building your own car from scratch to renting an electric scooter on the street. The architect has to be able to choose the optimal middle ground for their specific journey.
That's the perfect analogy. And that's a takeaway for compute. Compute Engine for maximum customization. GKE for open source container orchestration and avoiding vendor lock-in. App Engine for runtime speed and simplicity. And Cloud Run for container flexibility coupled with serverless efficiency.
That transition from running code leads us directly to the necessary companion, storage. I mean, applications need data persistence, but data is not monolithic. A photo, a transaction record, and an operating system file all have radically different storage needs.
Absolutely. And when we talk about storage in GCP, we are dealing with three core paradigms. The choice between them is dictated entirely by the access pattern and the latency requirement of your data. We have object storage, block storage, and file storage.
Okay, let's start with the utility player, the one that seems to pop up everywhere. The most ubiquitous and scalable storage service. Cloud storage.
Right. Cloud storage is GCP's object storage service.
Ah.
It's designed for massive quantities of unstructured data, things like images, videos, backups, logs, and it's a foundation for most data lakes. It's built for durability and availability at an astronomical scale, you should think. Global data bucket.
When you say astronomical scale, what are the hard numbers on something like durability? What does that really mean?
The standard promise for object storage like cloud storage is 11 nines of durability. That's 99.99999999999%.
So the probability of losing a file due to a hardware failure is just incredibly remote.
Vanishingly small. And this is achieved by storing the data redundantly across multiple disks, multiple devices, and often across multiple data centers within a region.
Now, crucially, this service offers tiered storage classes to manage cost. This seems vital when you're storing petabytes of data. Let's detail those cost and access trade-offs.
Yeah, this is where strategic cost management really happens. You choose a class based on how often you expect to access the data, and that choice influences your monthly storage cost and, critically, your retrieval cost.
Okay, break them down for us.
So first you have standard. This is for frequently accessed, hot data, think website assets, highly active data. It has the highest monthly cost, but the lowest retrieval cost, or no retrieval cost at all.
Makes sense. What's next?
Then you have nearline. This is for data you expect to access less than once a month. Think backups or data archives you might need occasionally. The monthly cost is lower, but there's a small fee every time you retrieve the data.
Okay, so you pay for access.
Exactly. Moving colder, you have cold line. This is for data access less than once a quarter. Disaster recovery archives are a great example. Even lower monthly cost, but a higher retrieval fee.
And the coldest.
That's archive. This is for long-term retention and regulatory compliance. Think 7-year tax records you can't delete but probably will never look at. It has the lowest monthly storage cost by far, but the highest retrieval fee and a longer retrieval latency.
So, if our media company stores their entire 4K video library in cloud storage, they can immediately save huge amounts of money by moving the older, rarely requested raw footage from standard all the way down to archive just by changing a configuration setting.
Precisely. The counterpoint, however, is that object storage is accessed via API calls, not a traditional file system mount. It is completely unsuitable for structured, transactional data that requires complex querying and indexing, and it's not for an operating system that needs block-level access.
Okay, which brings us to the next type. We have block storage, which is tightly coupled with our compute engine VM's persistent disk.
Exactly. Persistent disk is the high-performance block storage volume that acts as a virtual hard drive for your VMs. It provides the low-latency storage required for the operating system, for databases, and for application files residing on a compute engine VM. You should think VM hard drive.
And why is this distinction so important? Why can't I just run my operating system off of cloud storage?
Because operating systems require file system semantics and block-level access. They need the storage device to appear as a physical drive that can be formatted and mounted. You can't do that with an object store.
Right, and persistent disk has performance tiers too.
It does. You have standard, which uses hard disk drives. You have SSD for faster performance. And you have an extremely high-performance, extreme persistent disk for workloads that need massive IOPS input operations per second, like a high-traffic database.
Now, you mentioned a critical architectural limitation of persistent disk. It's about its geographical scope.
Yes, and this is a classic mistake. This is where architectures can fail if it's not accounted for. Persistent disk is strictly zonal.
Explain what that means.
A zone is a physically isolated data center within a larger region. So a persistent disk lives in one specific building. While this provides excellent resilience against most local faults, if our trading application, Global Trades, needs to access that exact same data volume from a VM in a different zone for a high availability failover,
It can't.
it cannot do it directly. If the zone fails, you have to rely on snapshots or replication to bring the data up in another zone. You cannot simply detach the disk from a VM in zone A and attach it to a VM in zone B.
That's a huge constraint to design around. And that zonal limitation, plus the need for multiple machines to access the exact same data set at the same time, often necessitates a network-attached file system. And that's where Cloud File Store comes in.
Right. Cloud File Store is GCP's Managed Network File System, or NFS service. It provides shared file storage that can be accessed by multiple compute engine VMs and GKE clusters simultaneously. This is crucial for applications that require POSX-compliant file access and shared visibility. The way to think about this one is shared network drive.
Give me a solid enterprise use case that specifically demands a shared NFS solution like this.
Think about a traditional lift and shift enterprise application, a complex content management system, or maybe a team of engineers sharing a centralized source code repository. They might have dozens of VMs running the application, and all of them expect to be able to read and write to the exact same shared directory of configuration files at the same time.
I see.
They use File Store to create that single shared file system that all those compute nodes can mount and interact with instantly. This service exists primarily to support those kinds of enterprise workloads that expect traditional file-based protocols.
So it's really designed to solve the data sharing problem that persistent disk cannot, but presumably at a higher cost than simple object storage.
Exactly. It's purpose-built for file-based protocols. If your data is object-based, like images or videos, or if it's structured like a database, File Store is the wrong tool for the job and most likely a much more expensive one. You have to match the data's access pattern to the service.
We've established where the code runs and where the files live. Now we dive into the most critical part of the application stack, the structured and semi-structured data managed through databases. The architectural choice here seems less about control and more about consistency versus massive flexibility and scale.
This is where we really see GCP making some philosophical breaks with traditional database management, particularly with services like Spanner and BigQuery. We need to contrast the requirements for transaction processing, OLTP, versus large-scale analytics, which is OLAP.
Okay, so let's start with the reliable, managed relational workhorse for online transaction processing, Cloud SQL.
Cloud SQL is GCP's fully managed relational database service. It supports MySQL, PostgreSQL, and SQL Server. Crucially, it handles all the mundane administrative tasks patching, backups, scaling storage, and configuring high availability. The simple way to think about it is managed MySQL Postgres.
And this is the default choice for the vast majority of standard web applications, right? We're talking user data, product catalogs, simple e-commerce transactions.
Yes, absolutely. It provides managed regional deployment with strong consistency, which is vital for transactional integrity. You don't want to sell the same product twice. However, it is constrained by the nature of traditional relational databases.
How so?
It's generally scaled vertically, meaning you give it a more powerful instance. And while it can handle high load, it can't inherently provide the global horizontal scale required by true hyperscale applications. And of course, being relational, it's not for unstructured data.
And that limitation on scale leads us directly to Cloud Spanner, which is often cited as GCP's true innovation in the database space. This is where you said the philosophical break happens.
It really is. Cloud Spanner is revolutionary because it solves a dilemma that database architects have faced for decades. The CAP theorem. The theorem forces a choice between consistency, availability, and partition tolerance. Spanner is a globally distributed, horizontally scalable, and strongly consistent relational database.
Which is supposed to be impossible.
It was thought to be yes. Traditional SQL sacrifices global scalability for consistency. Most NoSQL databases sacrifice strong consistency for scale. Spanner provides global linear scalability with strong consistency. The right way to think about it is global scalable SQL.
How on earth does Spanner achieve this strong consistency across multiple continents? That sounds like technical magic.
It's achieved through extremely tight synchronization using highly accurate atomic clocks and some very advanced synchronization algorithms across its global fleet of servers. This ensures that a transaction committed in Asia is immediately and reliably consistent with data views in Europe or North America.
Okay, give me the high-stakes scenario that justifies the investment in Spanner over, say, just a highly available Cloud SQL cluster.
Think about global financial institutions or high-demand payment processing systems. Let's imagine a company, Global Finance, that needs to store billions of transactions. They need massive scale and elasticity to handle peak demand, like on Black Friday. But they absolutely require strong data integrity or consistency across all their global operational centers.
Right. A bank can't have eventual consistency with your account balance.
Exactly. For mission-critical, high-transaction workloads where failure or inconsistency is simply not an option, Spanner is the architecturally sound, albeit premium, choice.
And the counterpoint is cost and complexity, I assume.
Correct on both counts. Spanner is significantly more expensive than Cloud SQL. For a standard regional application or a local e-commerce store, Spanner is complete overkill. You should only adopt Spanner when your requirements for global scale and mission-critical consistency cannot be met by standard relational technologies.
Got it. Okay, so when the requirement shifts away from that strong transactional consistency and more towards flexibility, speed, and handling dynamic schema changes, we turn to NoSQL. GCP offers Cloud Data Store and the more specialized, real-time focused Cloud Firestore.
Right. These are highly scalable, flexible, NoSQL document database services. They are perfect for applications where the data structure changes frequently or where eventual consistency is perfectly acceptable. They excel at storing things like user profiles, game data, and application settings. The right mental model here is flexible app data.
What specifically makes Firestore the modern choice, especially for highly interactive applications? It seems to be the one getting most of the attention.
Firestore is really designed for modern application development. It features automatic scaling and, most critically, real-time synchronization.
What does that mean in practice?
It allows your applications to listen to database changes and receive updates instantly without constantly pulling the server. So if Fast Launch builds a collaborative whiteboard app or a real-time chat feature, Firestore immediately pushes message updates to all connected users globally.
I see. That capability drastically simplifies the application code you'd have to write to get that real-time interactivity.
It does, a huge amount. It also integrates client libraries that manage things like offline support and security rules. You can define security rules that control who can read and write data directly from the mobile app or browser, moving security enforcement closer to the client. That's a huge win for mobile backends.
But the major limitation here is still the data structure, correct?
Yes. While they're incredibly flexible for application data, NewSQL document stores are terrible for complex multi-table joins or massive analytical workloads. They're optimized for retrieving and updating small chunks of data very quickly based on simple key lookups or indexes, not for finding global trends across petabytes of data.
Which means if you do need those complex global trends, you turn to the analytical engine of GCP, BigQuery.
Exactly. BigQuery is the fully managed serverless data warehouse service. It's a pure OLAP or analytical engine. Its architecture separates compute and storage, allowing you to run complex SQL queries over truly massive data sets. We're talking petabytes of information without managing any infrastructure at all, you should think. Analytics at scale.
The serverless nature here means you're not provisioning a colossal database cluster up front. You are only paying for the computational power needed to execute the query when you run it.
That is the core economic advantage. BigQuery is based on Google's Dremel architecture, which was designed for massive parallel execution. So Global Trades, our finance company, needs to analyze 5 years of historical trading data to spot market anomalies. Instead of waiting hours or even days for a report from a traditional SQL database, BigQuery can process those petabytes in seconds or minutes.
And the data structure it uses is columnar storage, right? Optimized for reading a huge number of records, but only for a few columns at a time, which is typical of analytical reporting.
Precisely. It maximizes efficiency for analysis. But the counterpoint, which must be repeated, is that BigQuery is not built for transactional workloads. You cannot use it to update a single user record with low latency.
Wrong tool for the job.
Completely wrong tool. You must use Cloud SQL or Spanner for transactional consistency and low latency operation. BigQuery is where data goes to be analyzed, not changed transactionally.
Okay? The compute, storage, and database services are the heart of the application, but they are completely useless without the nervous system that connects and secures them. We need to understand the fundamental services that provide that connectivity and access control.
And we start with the absolute bedrock. Identity and Access Management, or IAM. It's the single most critical security layer, controlling who can do what on the platform. The simplest way to think about it is security permissions. The goal is always to implement the principle of least privilege, granting only the necessary permissions for a task and nothing more.
How does GCP IAM structure these permissions? Because it can often feel like a dizzying matrix of policies and roles.
It can, but it breaks down into 3 core components that bind together.
Right.
First, you have members. This is the who. These are the identities. They can be standard Google accounts for users, Google Groups, or, very importantly, service accounts.
And what's a service account?
It's a non-human identity. It's used by applications, like a cloud function or a VM, to interact with other GCP services in an automated way.
Got it. Who, what, where. So who is members? What's what?
The what is roles. Roles define the specific permissions. GCP has very broad primitive roles, like owner or viewer. Then it has thousands of predefined roles that are specific to a service, like storage object creator. And crucially, it has custom roles, which allow you to tailor permissions down to the individual action level, which is how you achieve least privilege.
And the where.
The where is policies. These are attached to resources, an entire project, a folder, or even a specific storage bucket, and they're what bind the members to their roles on that resource.
The service account seems particularly important for automation. So if Fast Launch deploys their application on Cloud Run, and that application needs to write logs to Cloud Logging, it would operate under a service account.
Correct. The service account is the identity of the application itself. And if that service account is only granted the role of cloud logging writer, then that application can only write logs. It cannot, for example, delete data from BigQuery, even if an attacker manages to compromise the application.
So that granular machine identity control is what enables secure automation.
It's the key to it, yes.
Okay. These next services are the crucial glue, the infrastructure connectors that allow our components to communicate securely and efficiently, both internally and globally.
We start with the isolation layer. The Virtual Private Cloud, or VPC. This is your private, isolated network within GCP. It gives you complete control over routing, subnets, firewalls, and IP addresses. You should think your own cloud network.
What's unique about GCP's VPC implementation compared to other clouds? I hear this mentioned a lot.
The big one is that GCP VPCs are global by default. You define a single VPC network, and then you can create regional subnets within that network wherever you need them around the world.
What does that enable?
It allows VMs and services in different regions, say in Europe and Asia, to communicate privately and securely over Google's high-speed private backbone using internal IP addresses. You don't have to configure complex peering or VPNs to make that happen. It just works.
And securing that global network?
That's handled by firewall rules, which are also enforced globally at the VPC level. You define rules that control the traffic flow, specifying which services, IP ranges, or tags are allowed ingress, which is in, or egress, which is out traffic.
Once we have the network, we need to handle traffic distribution, which brings us to cloud load balancing.
Right. Cloud load balancing acts as the traffic manager. It's a distributed, software-defined service that ensures high availability and scalability by distributing incoming traffic across multiple back-end instances, whether those are VMs, containers, or functions.
And there are key distinctions in load balancing, right? It's not one size fits all.
No, not at all. The most common is the global HTTPS load balancer, which gives you a single IP address that works anywhere in the world, and it automatically routes users to the nearest healthy backend. Then you have regional load balancers for internal traffic or specialized protocols. It intelligently integrates with services like GKE and Compute Engine, always making sure that traffic hits a healthy, optimally performing endpoint.
And for global applications serving media or static files, latency is always the enemy.
Which is solved by Cloud CDN, Content Delivery Network. It caches your content images, static files at hundreds of edge locations worldwide. By serving popular content from a cache that's physically close to the user, it drastically reduces latency, improves performance, and reduces the load on your back-end compute services.
And the last piece of the networking puzzle.
That would be Cloud DNS, which is the managed service for your domain names and DNS records. It translates the human-readable web addresses like www.example.com into the IP addresses required for your network to route traffic correctly.
We've covered the foundation, but the sources underscore GCP's specialties in data and AI. Let's briefly touch upon the major offerings in those advanced areas.
Okay. In data analytics, if an organization is transitioning from on-premise Hadoop or Spark clusters, GCP offers Dataproc for managed execution of those exact workloads. For more sophisticated stream and batch data processing pipelines, the preferred modern tool is Dataflow, which provides a unified programming model for both.
And for real-time messaging.
For high-throughput, real-time messaging, connecting different applications and systems together, the primary service is PubSub. It's a highly scalable global messaging queue.
And Google's strength in AI is legendary. What's the unified platform for practitioners to actually build models?
That is Vertex AI. It is a unified platform specifically designed to streamline the entire machine learning lifecycle. Data preparation, model training, prediction serving, and monitoring. It really reduces the friction involved in taking an ML model from a concept in a notebook to a production-ready deployment.
And for the data scientists who just want to experiment.
For those who prefer a familiar notebook interface, there are also AI platform notebooks, which provide managed Jupyter environments that are pre-configured with all the necessary libraries.
Finally, you can't run what you can't see. The critical tools for observing the application's health monitoring and debugging.
Yes, the management tool suite is essential for operational excellence. Cloud monitoring gathers metrics and sends alerts based on resource utilization and application health. Cloud logging centralizes log management from all your services into one place. And for diagnosing performance issues in complex microservices, CloudTrace allows you to see how a single request traverses every single service in your architecture, helping you pinpoint bottlenecks.
We have dissected all the individual components. Now we reach the aha moment, seeing how these services actually integrate to solve real-world problems. We're moving from feature definitions to actual solution blueprints. Let's start with a typical high-volume modern architecture, the e-commerce website.
Right. An e-commerce site requires transactional consistency, rapid content delivery, and heavy retrospective analytics. This solution really showcases the necessary trade-offs between different compute environments and database types.
So how does the compute layer typically run a production modern e-commerce application, given the need for resilience and scaling?
Well, instead of going for maximum control with compute engine, the application logic often runs on a combination of highly scalable managed services. GKE is very often used for the core, mission-critical inventory, and checkout microservices.
Why GKE?
Because of its ability to scale containers rapidly and that portability advantage we talked about, you're not locked into a specific platform.
And the data. The product catalogs, user accounts, order information, that's all structured, and it requires strong consistency.
That's a classic use case for Cloud SQL, probably using the PostgreSQL or MySQL engine. It provides that managed relational consistency for the transactional processing.
What about all the images? The high-resolution product photos, videos, JavaScript files?
All of that static content is stored reliably and affordably in cloud storage. That bucket is then integrated with Cloud CDN to ensure those images load instantly for users anywhere in the world. That improves conversion rates by reducing latency. A slow site loses sales.
Of course. Now, once an order is placed, we often see asynchronous processing for tasks like sending a confirmation email.
That's the perfect domain for serverless events. The order placement in Cloud SQL triggers a message on Cloud PubSub. That message, in turn, triggers a Cloud function.
And the function sends the email.
Exactly. That short-lived function reads the order data and sends the confirmation email, or SMS. This keeps the core GKE application layer fast and decoupled from these non-critical background tasks.
And what about the crucial business intelligence, step analyzing millions of transactions to find trends?
All of that transactional data from Cloud SQL is continuously streamed into BigQuery via a data pipeline. The business then uses BigQuery to analyze sales data, predict trends, and optimize inventory. They can run queries over years of data efficiently, and it's completely separate from the live transactional Cloud SQL database, so analytics never slows down the checkout process.
E-commerce is demanding, but mobile gaming is just brutal high concurrency, zero tolerance for latency, and massive unpredictable scale spikes. This has to require a different approach, especially in the database philosophy.
It does. This architecture is absolutely dominated by the need for massive scale and real-time updates. The compute layer shifts very heavily to GKE. The game servers themselves run in containers managed by GKE, using its auto-scaling capabilities to instantly provision new game instances based on concurrent player demand.
And cloud load balancing is sitting in front of that.
Right, fronting all of it to distribute player connections efficiently to the game servers.
Why GKE over something like Cloud Run for the game servers?
Because game servers often require stateful connections. They need specific networking protocols like UDP or TCP, and certain resource guarantees that are just better managed within a full Kubernetes environment than a stateless, general-purpose serverless one like Cloud Run.
And the database structure. It must have to handle millions of simultaneous reads and writes for real-time game state.
This is where we move away from traditional SQL consistency for the core game data. Cloud Firestore is used for these real-time database needs. It stores player locations, scores, inventory, and dynamic game state. Its real-time synchronization ensures that all players see the current state of the game with minimal latency.
And how do they handle massive event flows, like in-game chat or activity feeds from millions of players at once?
That's high-throughput, low-latency messaging via Cloud PubSub. It's used to manage and process those in-game events and notifications instantly. It can handle that massive stream of events generated by millions of players.
And the large game assets, the textures, maps, sound packs.
Those remain safely and cost-effectively stored in cloud storage, globally distributed via CDN, just like in the e-commerce example. This entire architecture is built for elasticity and low latency interaction above all else.
Okay, finally, let's look at a pure data pipeline, taking raw, messy data from all sorts of sources and transforming it into clear, business-driving insights. This is a specialization that GCP is known to excel at.
It is. This architecture focuses on data flow and processing efficiency. It starts with a foundational location for all raw, untransformed data. This is almost always handled by cloud storage, acting as a massive, durable, and cost-effective data lake. Data is ingested here from various sources, logs, third-party files, database dumps.
So you have a lake of raw data. How do we wrangle that into a usable, clean format?
We need robust transformation tools. Cloud data flow is typically used for transforming, cleaning, and aggregating that data. It's powerful because it can handle both streaming data, like real-time website clicks, and batch data, like daily transaction files using the same code.
And once it's processed and validated?
The clean data moves into the final optimized destination for querying, BigQuery, which serves as the serverless data warehouse.
And since these data pipelines can involve dozens of steps, ingestion, cleaning, validation, loading, we need an automation layer to manage the whole thing.
Right, that orchestration is managed by Cloud Composer, which is GCP's managed Apache Airflow service. It handles the complex scheduling, dependency management, and monitoring of the entire data pipeline. It ensures that the raw data is cleaned and available in BigQuery exactly when the business needs it.
And from there, the business can connect their tools.
Exactly. The final insights, dashboards, even machine learning models are often built right on top of BigQuery, possibly utilizing Vertex AI to run predictive analytics on that massive historical data set.
This has been a true deep dive into the GCP foundational landscape. Let's just try to crystallize the core lessons for you, the listener.
I think we've established the strategic reasons to choose GCP, its inherited scale from Google's own services, its innovative AI and ML integration, and its unique user-friendly pricing models.
Right.
We then successfully map the three compute models: IaaS for full control with Compute Engine, PaaS for fast deployment with App Engine, and serverless for ultimate efficiency and portability with Cloud Run.
We also clarified the three core storage paradigms: object storage with cloud storage, block storage with persistent disk, and file storage with file store.
Most critically, we dissected the database choices, distinguishing between high-consistency relational databases like Cloud SQL and Spanner, high-flexibility NoSQL with Firestore, and massive scale analytics with BigQuery.
And I think the critical skill that you hopefully developed is architectural discernment. It's about choosing the right service based on the required control, the data access pattern, the desired scale, consistency requirements, and of course cost constraints. And we saw that clearly in our three architectural blueprints.
You now possess the foundational vocabulary and hopefully the strategic insights needed to begin designing intelligent, cost-optimized, and resilient solutions on GCP.
We've established what the services are and how they work together logically. But there's one final, fundamental concept that determines the real-world stability and resilience of everything we've discussed: location.
That's a great point. The foundation we've built today doesn't exist in some logical vacuum. It lives in a physical place. The next crucial step in your architectural journey is understanding GCP's regions, zones, and global services.
We touched on this.
We did. We've mentioned that persistent disk is zonal, that Cloud SQL is regional, and that Spanner is global. If you fail to account for geography in your designs, you sacrifice resilience. It's as simple as that. A single zone failure could wipe out your compute engine application if you haven't planned for it, and a poor regional choice can introduce excessive, user-frustrating latency.
So your final challenge, the thing we want you to mull over, is this. What assumptions are you currently making about your application's physical location that could drastically affect its availability during a service disruption? And how do you leverage GCP's multi-region and multi-zone deployment models to make your architecture truly resilient? That geographical understanding, that is your next deep dive.